All right, hello and welcome back once again to JIT 2021. And right now, ladies and gentlemen, it's now time that we are waiting for. The next is the last session of Corundum Symposium by the topic, Latest Advancements in Corundum Tasting by Dr. Michael Krzemnicki, the director of the Swiss Gemmological Institute, SSEF. Hello, Dr. Michael.
Hello, hello.
Can you hear me clearly?
I hear you clearly.
Okay. How the COVID situation in Switzerland?
We are in the midst of the Omicron wave, but I think it's getting better.
Okay, and I'm pretty sure that you are ready for the presentation, right?
That's true.
Okay, so I will hand over to you.
Okay, that's very kind. Thank you. Thank you.
Have a great day.
So, yes, ladies and gentlemen, dear organizers, it's for me a great pleasure and honor to be with you today and to speak about the current state and the latest advancement of corundum testing. So when testing rubies, sapphires, or any gemstone, we actually have to go through a procedure to finally answer the questions which are relevant for the trade and which are relevant also for consumers. And these questions we have to, what is happening here? We have to use methods, and it's very important to understand when we use these methods, it's a combination of methods which will lead us to answers. There is no magic black box where you just put the stone inside and you have a solution which gives you all answers on these questions. So by using a combination, we can finalize and we can give opinions of experts. And very important is to understand that microscopy and classic methods still nowadays are key to fully characterize and understand a gemstone. Now, the steps which I have shown you before, like identification, authenticity, the first step, identification, normally for corundum is very straightforward. The only question may arise about varieties, but this is not the topic of today, whether it's now pink sapphire or a ruby. So let's go directly to the next step, which is about authenticity. So whether a stone is natural or whether it is a synthetic stone. Now this was a topic mainly of the 70s and 80s. For gemmologists nowadays, we see much less frequently synthetic stones, and it might be more of a challenge for young gemmologists to recognize such stones. I just want to show you a case study, I would say actually rather a classic. What you see here are two microscopic images. You see on the left side a natural ruby from Madagascar, from Batamandri, showing these clusters of zircons. And on the right side, you have a situation of a flux melt synthetic stone, where you have similar looking clusters, which are, however, no zircons. So looking at this, it seems to be quite the same. And for sure, this synthetic stone comes along with papers telling that this stone is a natural stone, which is not the case. So we have to look into trace elements. And what you can see here in these two plots, we have on the left side gallium versus magnesium, and it's both axes logarithmic scale. We see actually that this case, this plotting in a field which is mostly or where the natural stones are found, together with some outliers of synthetic flux melt synthetic stones. But when we add the second plot, where we have vanadium versus elements which are normally coming from the crucible or from the flux melt itself, like rhodium, platinum, lead, and bismuth, then we clearly can identify this stone or such a stone as a synthetic stone. The next step is to talk about treatments. Now, treatments, everybody knows there is a large range of treatments known for corundum. And for some of these treatments, the detection is not straightforward, but rather challenging. So to go into detection of treatments, we again have access, and this is a very aesthetic side of this work also, we have access to microscopy. That is very important, and as you can see here, these are very classic inclusions which we see of so-called atoll structures in an orange sapphire, and even on the same stone, some parts where you see a molten surface. So this stone definitely is heat treated, which we can tell by microscopy. Another way to work with such a stone is to work on inclusions. And here we have a figure showing the change in the Raman spectrum on zircons related to a heat treatment, starting from a very metamixed state where the peak is very broad, and due to the heat treatment, this peak becomes more and more narrow. Now, this is a very useful criterion and can be used for corundum, which is heat treated at rather high temperatures, let's say 1,200, 1,400, and even more. However, and this is the next slide, it is more challenging when we talk about the low temperature heat treatment. What you see in this plot is actually the peak position in the horizontal axis versus the full width half maximum of the main Raman peak of zircon inclusions in corundum. And the pink spots represent unheated stones. And you see some of these samples in the color range from pink to purple from Ilakaka in Madagascar. And you see a large variation of these peak sizes. And when we add on top of this stones which have been heated at rather low temperature, which are the yellow points, we see quite a strong overlapping. So it means this criterion for this low temperature heating below 1,000 degrees, it's not a clear-cut situation anymore. It's rather a gray area, overlapping area. So it does not help us so much in this respect. But we have access also to other tools, and for this, for sure, we can talk about infrared spectroscopy. Infrared spectroscopy is definitely useful also for detection of low temperature heated rubies and sapphires. As we can see here, it's a series of OH-related peaks, which is present. Finally, even the same peaks may be present in unheated stones, but it's the precise position of these peaks. And by this, it's possible to make a separation into stones which have been heated and such stones which have not been heated. What you see in the picture is actually a ruby of very exceptional quality. And what you see in the corner is a bluish zone. This Mozambique ruby, such material has been and is still heated at low temperatures in oxidizing conditions to finally get rid of this blue zone. When you look at the stone, you will not see this blue zone as you see it here in this transmission picture. If we look about treatments, another example would be, a classic example would be beryllium diffusion treatment. To detect this treatment, normally we need a tiny amount ablated from the stone, so to be able to analyze it chemically. And you can use, for example, lips, as you see in this spectrum, with a beryllium emission line, or laser ablation ICP mass spectrometry. This is just to show you the challenge. We at SSEF work closely also with the Swiss watch industry, and here we talk about very tiny stones, millimeter size. And the question is, what has happened to these stones? Are they natural, synthetic? Is there some treatment applied to these stones? And what we have here is actually a series of samples, and the mountain range you see in the background is actually the beryllium concentration, which is present in these stones. And these stones, in fact, have been diffusion treated by beryllium. What we have to monitor this situation are elements like tantalum, tin, niobe, so-called high field strength elements, and they are all very low, even below detection limits, which indicates that this beryllium is actually due to a diffusion process and not linked to any kind of nano inclusions, which have brought in some beryllium naturally into the stones. And finally, we go to the last step, which is about origin, geographic origin of a stone. What you see here is sunset at Mogok, a beautiful place. And when we talk about the origin, we have to understand that deposits of colored stones are commonly related to large-scale geological systems. And just to pick out one, we have here a scheme how India has collided, the Indian plate has collided with Eurasia, and which has then resulted in the formation of the Himalayan orogeny, and as such of some of the most important sources for colored gems. And what we can say also is that this is a rather young geological event compared to the Pan-African metamorphic event in, let's say, East Africa, Sri Lanka, and Madagascar. Now, looking at an origin of a stone, again, we come back to the fact that microscopy remains today still very important, because there may be some very clue found in a stone, as here a paugasite needle in this Kashmir sapphire. But then we have also access again to look, for example, at the structure of inclusions. And what we have here is just two Raman spectrum of zircon inclusion in sapphires. And as you can see, there is a huge difference between sapphires from Madagascar, like Ambatonra, where you have a very metamic zircon inclusion, so very broad peaks, compared to Kashmir, which shows very narrow and well-formed Raman peaks. So this is a very useful way to separate these stones, even if they visually look very similar. And here is just a plot when we take in more origins. This is a publication which we have done together with Venture and from the Gubelin lab, showing you the Raman peak position versus the full width half maximum of the main zircon Raman peak for different origins. And you can see that let's say, Mogok, Myanmar, and Kashmir zircon inclusions all show very narrow shape. So they are blue and green, and then you have Sri Lanka and Madagascar with much larger full width half maximum. If you want to have access to chemical data, then at SSEF we use an instrument called GemTOF. This is actually laser ablation inductively coupled plasma time of flight mass spectrometry. And different to the more common quadrupole mass spectrometry, where you actually have to pre-select elements which you want to measure, and then you have a peak hopping mode, so you measure one element and then the next and then the next. With GemTOF, you have a snapshot. You have the full spectrum of all isotopes at the same moment, and by this you have much more information for sure. Now with this instrument, we are analyzing corundum and other gemstones also to find answers about origin. But the problem with corundum is that these stones actually have a very, let's say, dense structure, and as such offer very little option for elemental substitutions. This makes identification, or let's say plotting, difficult, because we have not much options, and this is very different to emeralds, where you have a structure which can accommodate a lot of different elements inside. So what you see in this three-dimensional scatter plot with the elements iron, vanadium, and gallium is an overlapping situation. We can see a blue zone, and this is where we have sapphires from Kashmir, especially in this large cloud, the very fine quality sapphires from Kashmir. But again, it's quite difficult to work with this. So we have to try to use statistical methods. And by using statistical methods, what we try is to have a clear pattern to be able to make separations. So starting from just two elements, scatter plots, gallium versus magnesium, and we have only Kashmir and Madagascar sapphires chosen, we can start in a first attempt with a linear statistical approach, PCA analysis, still a large overlapping, or, and that's what we have gone into, nonlinear, unsupervised machine learning algorithm. So we use machine learning to get a better answer on origins. And this is also presented in a paper which we have published in the Journal of the Royal Society of Chemistry last year. And the case study there, which is presented, is about emeralds. And what we see in these emeralds is by using this approach, we really can create distinct clouds for different origins. And the red one here is Columbia, just to show you this. And to end up, finally, we can talk about the age of a stone. And we can talk about age dating, which is relying on radioactive isotope, for example, uranium, which then transforms or decays to a stable lead isotope. This is the common, normally used way to go through. And this is a method where we finally can say something about the age of formation of the stone, but definitely also it helps us in some cases to say something about the origin of a stone. At SSEF, we use plenty of different inclusions like apatite, rutile, zircon, xenotime to do age dating. Important is that this inclusion is touching the surface, is at the surface. Only by this we have access with our GemTOF instrument. Now, when we analyze zircon precisely, we will see that even if the grain is very small, very often it's not homogeneous. So we have a core which might be older than the rim which formed at the same moment of metamorphic event when the sapphire or ruby has formed. So we can have different ages depending on where we measure actually in this zircon grain. Now, when we look, however, on gemstone deposits, and as I said, Himalayan origin or Pan-African, this is such a huge time difference, so this doesn't matter so much. As we can see here, we have two similar looking sapphires, and one has a zircon inclusion which is 560 million years old, and the second one has an inclusion 25 million years old, which are both very clearly fitting for their relative origin. So by this, we can clearly exclude that the Kashmir sapphire has formed in Sri Lanka, and also the opposite, the Sri Lankan stone has not formed in Kashmir. So with this, actually, I want to finish my presentation. I hope you have had some insights in current status and latest advancement in corundum testing. And I thank you very much for your attention. Thank you.
Thank you so much for an informative talk to Dr. Michael. And next, we will be moving on to the GIT conference. In this session, we also have the Thai and international experts who are going to give us more details. And next is a live conference by Mr. Richard Hughes, Senior Vice President, Lotus Gemmology. He will tell us more about the details of the challenges of describing colored gemstones.